I was always interested in how things worked, or rather perhaps what was underneath what worked. When I got here, I noticed the hot springs in New Zealand, the first thing any tourist noticed. And I guess I was fascinated by the knowledge that there were organisms living in those hot springs. This was at a time when enzymes, which are the machinery which make cells work, were generally not expected to function at those high temperatures.
A small band of scientists, this primordial scene is a source of untold wealth. Samples taken from the hot springs are brought to the University of Waikato, home of the biggest thermophile research unit in the world.
People have said, well, how is it that these organisms are able to survive these very high temperatures? This is extraordinary, very wonderful of these organisms to manage that. It now seems actually more likely, from work that's been done over the past 5 years or so, that life may actually have originated under these conditions. And a more sensible question to ask is, how is it that life actually manages to survive the frigidity of what we now think of as room temperature? It became apparent to us that these enzymes had applications, and when that lifted off, as it were, we got a lot of commercial money, and that enabled us to build up a research group and to begin to look more widely at things, not just at the applications. More and more we saw about enzymes and their ability to survive quite extraordinary temperatures that work quite well at 75 degrees. So how high can enzymes really work? Well, in the end, we pushed the working temperature of enzymes up to 135 degrees centigrade. At that point, we thought, well, if we can go that high, how low can we go? The general understood lowest temperature was about -5, which we used cryosolvents, and by designing a few new ones, we were able to get down to -100 degrees, and they worked just fine. Did a detailed study with collaborators using neutron beam spectroscopy at the molecular motions of enzymes, and we found that in fact we can see the correct molecular motions down to about -170 degrees. Now we were only actually able to measure activity properly at -100 because we couldn't find a suitable liquid that you really need to make enzymes work. I don't think this means that the maximum and minimum temperatures for enzymes to operate is somewhere between -100 and +135. Those temperatures are really limits on the experimental conditions we could use to properly measure the enzyme's activity. I personally think that we'll see enzyme activity well outside those limits, and very possibly life outside those limits as well. We formulated a model, and then we actually tested the model on 30 different enzymes of a wide variety of types. That's the key. Was this something that was just happening with the enzyme we looked at, or was it happening in all enzymes? I guess really, to be quite honest, to be our surprise, we found that it was happening for all enzymes. So this is a universal factor for enzymes. When you sort of find out things like this, you think, oh, I didn't expect that. And it's just, life is full of surprises, and in science, they're really inspiring surprises. I've collaborated with an awful lot of applied scientists, both in companies and within government agencies, and I have great admiration for them. They work within constraints that most university scientists don't experience, restrictions because of commercial imperatives, politics, whatever. And I think being a university scientist is an incredibly privileged position, and I've been very grateful for being in it.